Welcome to the Deep Dive. We're zooming past the headlines today, getting straight into something really mind-blowing out there in the cosmos. We're tackling a kind of cosmic riddle. It's about neutron stars. People often call them dead stars.
Right. But they're hardly lifeless.
Exactly. So the question is, how do these incredibly extreme objects, especially when they're orbiting with another star, how do they actually generate all that immense power?
It's a fantastic question, and one that keeps astronomers busy.
So today we're taking a really close look at a specific one. It's a rapidly spinning neutron star, nicknamed J1023. It's way out there, about 4,500 light years away.
A fair distance, yes.
And recent observations, using some seriously powerful telescopes, including NASA's Imaging X-ray Polarimetry Explorer, IXPE, they've basically unearthed a pretty big surprise about this pulsar. And this isn't just tweaking a minor detail in a theory. It seems like it's fundamentally shifting how we understand these cosmic powerhouses, how they interact, how they blast out radiation.
It really is a significant finding.
And for you listening, it kind of highlights how much we still don't know, even about the most extreme things out there, and how just one discovery can flip our whole understanding. So let's dig in.
Let's do it.
Okay, so J1023. It's a neutron star. The super-dense core left after a giant star explodes. We know that. But what makes this one really compelling is it's in a binary system. It's got a little companion star orbiting with it.
Right, a low-mass companion. And this specific neutron star, J1023, it's an absolute speed demon. I mean, it's spinning incredibly fast. We're talking around 600 times every second.
Wow, 600 times a second.
Per second, yeah. That's why we classify it as a millisecond pulsar.
That speed is just, it's mind-boggling. You try to picture that, right? An object the size of a city spinning that fast?
Yeah.
It really puts the extreme cosmic objects, doesn't it?
It certainly does.
But then there's another label. It's also called a transitional millisecond pulsar. What does that actually mean? Does it, change form?
Transitional, yeah. That's precisely what makes J1023 so special and so rare. It's one of only 3 known like it.
Only 3.
Okay. And transitional means it has this unique ability to, well, clearly shift between different states of being almost.
States? Like what?
It can be in an active phase where it's actively pulling material, feeding, you could say, from its companion star. And when it does that, it blasts out jets of radiation from its poles.
Okay, so that's the active state.
Right. But then it can switch, it can transition into a more dormant phase. And in that phase, it behaves more like a standard pulsar, just sort of quietly emitting radio waves that we can detect.
So it flips back and forth.
Yeah.
That makes it a kind of cosmic laboratory then, for studying how these things evolve.
Exactly. It's invaluable. Maria Cristina Baglio, she's a researcher at INEF, the National Institute for Astrophysics, put it really well. She said, transitional millisecond pulsars are cosmic laboratories that help us understand how neutron stars evolve in binary systems.
Makes sense.
And J1023 is, as she said, a particularly valuable source of data, just because those transitions, those shifts between states are so clear we can really watch it happen. It's a benchmark.
So when you picture this dead star feeding on its buddy, the companion star, you usually think of the material getting stripped off, right?
Yeah.
And forming this swirling disk around the neutron star.
The accretion disk, yes. That's the standard picture.
And that disk gets super hot and radiates energy across the whole spectrum as the material spirals in. That's like the common idea of how these things shine.
That is the common picture. But here's where J1023 throws a curveball. These new findings, they suggest something else is the primary driver, at least for this object.
Something other than the accretion disk glowing.
Exactly. It turns out the radiation we're seeing from J1023, especially in X-rays and optical light, seems to be dominated by the impact of its own incredibly powerful particle winds.
Particle winds, so stuff blasting out from the neutron star itself, not just stuff falling in.
Precisely. High energy-charged particles streaming away from the dead star. Think of it less like a cosmic vacuum cleaner sucking stuff in, and maybe more like a cosmic pressure washer blasting outwards. So the wind hits something. It seems the wind slams into the material that is still being pulled from the companion, maybe material in the outer parts of that disk or just nearby. And that collision, that interaction, is what's generating the bulk of the light we see, especially the polarized light.
Okay, so the wind is the main engine here, not the infalling stuff itself. And you said this confirms an earlier theory.
That's right. There was a theoretical model suggesting these winds could be really important, but getting direct evidence was tricky. This research provides that evidence.
That feels like a pretty big shift from the usual accretion disk story. How certain are scientists about this? I mean, what really convinced them?
Well, the confidence comes from the specifics of the observation, particularly the polarization data. It just didn't fit the standard accretion disk model very well. The wind model, however, explains the observations much more neatly.
Right. So let's unpack that. How on earth do scientists figure this out? Peering 4,500 light years away at these tiny, incredibly energetic things. What was the technique?
It really took a combination of cutting-edge tech and a clever approach. The team used several heavy-hitting instruments.
Like IXPE, you mentioned.
Exactly. NASA's Imaging X-ray Polarimetry Explorer, IXTE. That was crucial because it can measure the polarization of X-rays, which is a very specific property of light.
Okay, what else?
They also brought in the European Southern Observatory's Very Large Telescope, the VLT, down in Chile for optical observations, and the Karl G. Jansky Very Large Array, the VLA, in New Mexico for radio waves.
Wow, that's quite the arsenal. X-ray, optical, radio.
And importantly, it was the first time anyone had done a survey like this on a binary X-ray source, looking at polarization across all those bands, X-ray, optical, and radio simultaneously. That multi-wavelength polarimetry, that was the key.
The coordinated attack, basically.
You could say that. It allowed them to build a much more complete picture than looking at just one type of light would allow.
So what was J1023 actually doing while they were watching it with all this gear? Was it in its active feeding state or the quiet pulsar state?
Good question. During these observations, it was actually in what they call a low luminosity active phase. So it was active, pulling some material, but not at its absolute brightest.
And this phase had changes.
Yeah, it was characterized by these rapid flickers, changes between different X-ray brightness levels, which is actually useful. It gave them a dynamic system to observe, showing how things changed.
Okay, so we've got the setup, the telescopes, the state of the pulsar. Now the crucial clue. Polarization. You said IXPE measured X-ray polarization. What exactly is polarization and why is it the smoking gun here?
Right. Polarization. Think of a light wave traveling towards you. It's oscillating, vibrating. Unpolarized light, like from a standard light bulb, vibrates in all directions randomly. But polarized light is organized. The vibrations are aligned, predominantly oscillating in one specific direction or plane. How much it's aligned and in which direction tells you a lot about the environment where the light was created or what it passed through.
Like wearing polarized sunglasses to cut glare?
Exactly. That's the same principle.
Yeah.
Sunglasses block light polarized horizontally, which is how glare off water or roads is often polarized. Here, we're using the polarization from J1023 to figure out the physics happening near the neutron star.
So what did the polarization measurements actually show? What did IXPE see?
This is where it gets really interesting. IXPE found that about 12% of the X-rays coming from J1023 were polarized.
12%. Is that a lot?
It's huge. For this kind of system, an X-ray binary, that is the highest level of X-ray polarization ever seen. It's really significant.
Wow. Okay, so very aligned X-rays. What about the other telescopes, the VLT and VLA?
For comparison, the radio waves measured by the VLA showed only about 2% polarization, and the optical light seen by the VLT showed even less, just 1% polarization.
Much lower. So 12% in X-ray, 2% radio, 1% optical. But there was something else, wasn't there? Something about the direction.
Ah, yes. This is the clincher. The critical discovery was that the direction, the angle of polarization for that faint 1% optical light was oriented in exactly the same direction as the angle of the highly polarized X-rays.
The same direction. Why is that alignment so important? What does that tell us?
That alignment is the key. As Alessandro Di Marco, another INAF researcher involved, pointed out, this remarkable alignment between optical and X-ray polarization strongly implies there's a common mechanism generating both types of light.
Ah, I see. If they were totally different processes, you wouldn't expect them to line up like that.
Precisely. It wouldn't make sense for, say, the inner hotter part of an accretion disk making X-rays and a different, cooler outer part making optical light to just coincidentally have their polarization aligned perfectly.
So what does explain it?
The particle wind model does. This alignment provided the direct evidence, the smoking gun, confirming that these polarized emissions, both the X-ray and the optical, are generated when the pulsar's powerful particle winds slam into surrounding matter, probably in the disk. And crucially, it shows that this wind interaction is the dominant source of that polarized radiation we see.
So the wind is painting both pictures, X-ray and optical, with the same brush, so to speak.
A very energetic brush, yes. That's a good way to put it.
Okay, let's connect this back to the bigger picture then. What does this whole deep dive into one specific kind of weird star, J1023, really teach us about the wider universe, about how these exotic objects actually work?
Well, it's a major step in understanding what truly powers pulsars, especially those in binary systems. It fundamentally shifts the focus, suggesting that the pulsar's own output, its wind, can be more important energetically than just the material it captures.
It's not just a passive recipient of fuel, it's actively shaping its environment with its own outflow.
Exactly. This could change how we model the evolution of these binary systems, how energy is exchanged, and potentially even how these systems influence their surroundings in galaxies.
And it highlights the power of new instruments, right, like IXPE.
Absolutely. IXPE's sensitivity was critical. Detecting and measuring polarization, especially for relatively faint X-ray sources like J23 in this state, is incredibly challenging. Without IXPE, we wouldn't have this key piece of the puzzle.
It really was, as DeMarco said, an ingenious way to test theoretical scenarios, using polarization across different wavelengths.
Yes, it's a powerful technique that we're only just beginning to fully exploit. And the research, for those interested, was published July 1st in the Astrophysical Journal Letters.
So, to recap, we've seen how this one unique neutron star, PSR J1023+0038, has basically forced astronomers to rethink how these cosmic powerhouses work. It's shown us that their own powerful particle winds can be the main show, the dominant source of radiation, not just the stuff they pull off their companion star.
A really fundamental insight from a fascinating object.
Which leaves us with a pretty provocative thought, doesn't it? What other basic assumptions that we hold about the most extreme objects in the universe might just be waiting to be overturned? Especially as we keep building new tools, more sensitive instruments that let us observe the cosmos in ways we just couldn't before. Think about it, how these tiny, subtle clues, hidden within light itself, like its polarization, can end up revealing the most powerful, hidden forces shaping things across the vastness of space. What else is hiding in the light?
It's what keeps us looking up. There are always more secrets out there.